Today we're going to start our discussion with some of the applications of electrochemistry, and we're going to begin with probably the most common and most well-known application, and that is batteries. So we're going to start off by just going over some of the basic battery types. So we're going to start with what we call a dry cell battery. So what's shown here is some of the original type, which is sometimes known as an acidic dry cell battery or just a dry cell battery. So if we remind ourselves, a battery, right, is just a voltaic cell that has been packaged in a very compact or convenient way, right? We still have an anode, and we still have an anode half cell and a cathode half cell, electrodes, etc. So if we kind of go over this one, so in this kind of battery, our anode here is made of typically of zinc, could be magnesium, and it's located on the inner shell of the battery. So if you look on the sides of the case and the bottom of the case, right, this is where you're going to find your zinc anode. Right? And of course, at this point, your zinc is being oxidized, right? And this is the half reaction here. And so if you look at a battery, right, the negative terminal, right, is going to be that bottom part of the battery. It'll be labeled with your negative terminal. The cathode, right, runs right down the middle of the battery, right, and is typically made of a graphite rod, right? And it pops up to have the positive electrode, the positive contact, right, where we would attach our circuit, right, the cathode terminal, and that little dimple at the top. Now, this cathode rod is typically coated or somehow impregnated, built into the graphite with a manganese dioxide, and we have our reduction reaction here where the manganese is reduced, as we can see, from manganese positive 4 here to manganese positive 6 here. So we have our anode and we have our cathode. Now the salt bridge, right, the rest of the battery, right, is this paste out here. And this is typically made up of, in this type of battery, some ammonium chloride, perhaps some other stuff, but it's that ammonium chloride that really provides the electrolyte, right, and salt bridge type, and allows for the movement of ions. Okay. Now, this will put off a cell voltage of about 1.5 volts. So, now, as we're going through these different examples of batteries, I expect you to know the basic structure of the batteries. I don't necessarily expect you to be able to write out verbatim the half reactions, maybe a zinc oxidation, but I would expect you to know essentially what they're made of and what the voltages are, and other sort of important applications of that particular battery type. So these dry cell batteries are about 1.5 volts. Now, if you haven't noticed from the picture, this is the basis for all of the batteries that we use or have used sort of in everyday usage. These are our classic A, AA, AAA, CD type battery cells. And if you look on those, they will all have the negative terminal at the flat bottom. The positive terminal will be at the little bump on the top. And if you look on the side, they will say that they're putting off 1.5 volts. Now, this was the original type. Most modern batteries are what we call alkaline dry cells, which are the same basic battery. They have the same anode, they have a zinc anode. The one thing that's different is that they've been turned into a basic environment. are, quote, alkaline. So they're the same as the basic acidic cell, but your electrolyte now is a very basic environment, particularly some sort of metal hydroxide, like a potassium hydroxide. But you can see our basic reactions, our oxidation of zinc, and our reduction of manganese is essentially the same. So, same basic construction, just we've turned it into a basic environment. Now, why? Well, the advantage is the alkaline cell gives me a longer shelf life, has a longer working time, and we get less corrosion of our metal, right? And sometimes that acidic environment, remember, that can eat away at the metals, the zinc in this case, over time. So we have our classic dry cell, and more commonly alkaline dry cells, which put out about 1.5 volts. And again, these are the basis for our common batteries. Now, of course, one of the disadvantages of these batteries is that they are single use, and they run out over time, right? As the chemicals, right, as the anode and the cathode, specifically the anode is used up, and the cathode is used up, right? The batteries will start to die, right? We start to build up charge, use up, we start to reach, right, a point where the battery is less reactive, right? That spontaneous electrochemical reaction as we build up product is not going to be as favored. So we can now turn our attention to look at some rechargeable batteries. Now, the most well-known rechargeable battery is probably one that maybe you don't first think about, and that is the lead storage battery. And of course, this is the common battery that we use in our cars or motorcycles or other vehicles, right? This is based on what's called the lead storage battery. Now, one interesting thing, right, is that the classic car battery, right, as you may know, is a 12-volt battery. But a lead cell, a lead storage battery cell, is a 2-volt cell, right? So just like our alkaline cells are 1.5, a lead storage battery puts off about 2 volts. So this allows us to talk about a basic rule of batteries, which is if we want to use a certain type of battery to get more voltage out, we can hook them up in what we call series. So we do this in a car battery by hooking together 6 2-volt lead storage cells right in a row. We package that in a nice neat package, so we end up with a 12-volt battery. Now, in a dry cell battery, right, we do this as well. We don't necessarily package them because we want the flexibility. But if you notice your calculator or different things that you put these AA or AAA batteries in often require 3, 4, 5 batteries, right? Flashlights, etc. What we're doing is hooking those up in series, right? We're hooking them up so that they touch each other, positive to negative, so it's like using one big battery with adding their voltages together. So if we hook up, 4 alkaline batteries, we can get the equivalent of a 6-volt battery cell. So we'll often do that. Okay, but let's turn our attention back to the lead storage battery. It's a fairly simple construction, right? It is an electrolyte made up of sulfuric acid, right? So this is what is commonly referred to as battery acid, right? So these are in a bath of very strong acid. Your anode is lead being oxidized to lead 2. Right? So we got lead 0 going to lead 2. In this case, lead sulfate with the sulfate ions that are present in your electrolyte. Your cathode is also lead. So this is one of the interesting effects of this battery is that both the anode and the cathode are lead, and that lead is coated with lead oxide. Now, if we look closely, right, this lead oxide would be a +4 oxidation state. So at the cathode, what happens is this lead oxide is reduced down to lead +2 in the form of lead sulfate. So notice in this battery, the product of the oxidation and the reduction are the same. So in both batteries, you're making lead-2 sulfate. So as this battery is running, you're going to make a lot of lead-2 sulfate solid in this battery, and that can then be converted back to either lead-4 in the form of the oxide, or back to lead metal at the anode. So as mentioned, these are rechargeable. So when you recharge a battery, you have to apply a voltage. So if they're spontaneous in the discharge, right? So if the discharge is spontaneous, of course the recharge would be non-spontaneous. So the way we get this non-spontaneous reaction to go is we apply a voltage, and that voltage has to be equal or greater to the voltage of the battery. Right? So we need to apply a voltage, and again, if you apply that voltage, you essentially force the reaction to go backwards. So we can drive the reaction back to where we want it to go. So, basic lead storage battery and used in automobiles. So, in a car, right, we're doing this recharging while we're driving. Right? We typically only use the battery to start the car and some maintenance things along the way, radios, etc. But for the most part, right, we're using it to start the car, and then during the driving purpose portion, we're recharging that battery back up. Okay, so lead storage battery. Now, we're going to discuss a couple of types of rechargeable batteries that have been designed to replace alkaline batteries. So the original version of this was something called a NICAD battery, or a nickel-cadmium battery. So again, these are alkaline cells. Right? They have KOH as your electrolyte solution. The anode here is made up of cadmium metal being oxidized, and your cathode, and this is where I think it's from, is a nickel compound. And so you have your oxidation of the cadmium, goes from cadmium 0 to cadmium +2, 2-electron oxidation, and your nickel goes again from nickel oxide, where it's nickel +4, to a nickel hydroxide, where the nickel is +2. So these put off about 1.3 volts, so a little less voltage than what we see in an alkaline cell, but not a whole lot. Now, these are great batteries. These were made, you might remember, in various forms to replace AA, AAA, larger types of batteries. But they are rechargeable, of course. They have a long life. They're relatively lightweight. Now, these did have recharging issues. You had to be very careful when you recharge them. You didn't want to overcharge them. So these were kind of finicky in the recharge process, which could shorten the battery life. Now, the other main issue with this type of battery is the toxicity, right? The cadmium is toxic, and this had a lot of issues with disposal. So these batteries were eventually replaced by what's called a nickel metal hydride battery. So very similar battery. Again, it has a KOH electrolyte, so it's another alkaline cell. The cathode is the same as what we saw in the nickel NICAD battery, but we've replaced your cadmium anode with a metal hydride. So this is some metal, right? And that metal differs depending on the brand and so forth. But the key part is it has dissolved hydrogen, or has hydrogen incorporated into the metal, and that hydrogen is what undergoes the reduction. So we're seeing essentially a hydrogen reduction here, or oxidation. So we get oxidized from hydrogen 0 to hydrogen plus 1, and we have that same nickel oxidation, nickel reduction from 4 to 2 that we saw in the NICAD battery. So for your oxidation, you're going from hydrogen 0 as part of our metal hydride complex to hydrogen plus 1 in the form of water. Again, very similar qualities, has about the same voltage, 1.3 volts. It's of course rechargeable. You've gotten rid of the toxicity issue by replacing the cadmium. So again, we have long life. These are fairly lightweight again, much more environmentally friendly, and they actually have a greater what we call energy density, because these metals are lighter weight than cadmium, which is a fairly heavy metal, and so you can get the same amount of voltage out at a lighter mass. So that's where we're getting this energy density measurement. So our last example of a true battery is going to be sort of the most recent type of common rechargeable battery that's sort of being used more and more. And this is what we call a lithium-ion battery. Now, this has a lot of commonalities with the batteries we've seen. It functions on sort of fundamentally a different way, though. So the electrolyte, again, KOH, or some sort of basic environment. Your anode is graphite, so you can see the graphite sheets here, impregnated with lithium ions. So these lithium positive 1 ions, right, are going to be located between the sheets of the graphite. So your cathode is a lithium transition metal oxide. So it's going to be some sort of transition metal with lithium incorporated oxides, such as lithium cobalt oxide. Now, it is actually the transition metal here, like the cobalt, that undergoes the reduction. So when this battery operates, when it's hooked up, what we see is a spontaneous flow of lithium ions when we undergo the discharge first. So you hook this up, and at discharge, you get a spontaneous flow of these lithium ions from the anode to the cathode. So if we look here at this graphic, when you're discharging, lithium ions are flowing this way, right? And so you get lithium ion migration. Now, the leaving of that positive charge triggers a corresponding release of negative electrons that will travel up here. So we can imagine lithium ions flowing this way, and the electrons then leave to flow this way. So the positive charge is leaving. This causes a loss of negative charge and the electrons to move. And the lithium ion ends up over here. and that arrival of the positive lithium ion causes the reduction of your transition metal, right? Causes your transition metal to lithium ion, the electrons come in here, and the transition metal takes on those electrons and undergoes reduction. And of course, with discharge, the opposite happens, right? The lithium ions flow back to the anode, which results in a lot of the electrons going back in reverse, and you reverse the process. So this is a really, really common type of battery now that's finding a lot of use, especially in portable electronics, like cell phones and laptops and iPads and all of that good stuff. They have a very long life. They are extremely light, right? If you look at the lithium, it's a very lightweight metal compared to a lot of the metals that we're using in these other batteries. It's more environmentally friendly than some of the other batteries. It has a big energy density, and it has a much larger cell voltage than what we've seen in any of these other batteries, about 3.5 volts. So it's found a lot of applications in potable electronics that have more and more demand for higher voltages. Okay. So these are some of our batteries. Now, we're going to look at one other member of this battery family, if you will, and that is what's called a fuel cell. Now, before we do that, let me just take a look at these batteries to compare sort of where we are. So we've mentioned along the way energy density, and so I just want to point out, right, the lithium ion has by far the greatest energy density here, right? Because of the lightness of the lithium and the high voltage we can get out of here, we're able to get a lot of energy in terms of watt hours per kilogram. So this is an electrical energy unit. You might remember kilowatt hours when we talked about electrical units. This is sort of a variation of that per mass. And so what this is saying is for the same mass of battery material, we can get more energy out. And so that's going to be highest for the lithium ion because we have very lightweight but high energy output. NICAD is pretty low. Right? Sometimes lithium metal hydride can be upwards of twice the NICAD battery, and then lithium ion is going to be, the best here. If you look at the lead storage, extremely low lead mass. If you ever see one of these batteries, they're very heavy, and for the output that you get, right, you're getting a fairly low energy density, right, from your lead storage battery. I mentioned that the NICAD battery had a finicky recharge, right? You had to be really careful on the recharge, right? This is the overcharge tolerance, right? You don't want to charge it past maximum, right? So we have mechanisms to shut these down, but this is sort of intolerant of that, whereas these are very tolerant, right? And you've, I'm sure, experienced the fact that you can essentially charge your cell phones, etc., in sort of any way that you want to anymore, right? You charge them while they're full, charge them when they're empty, charge them halfway, they're very tolerant of all kinds of ways that you charge them. You need to make sure that you charge them with the right voltage, but otherwise they're pretty flexible on their charging. Now, in this section, last thing that I want to kind of talk about is these fuel cells, right? So a fuel cell is like a battery, but the difference is that a battery is a packaged item, right? It has a set amount of fuel, and when that fuel starts to run out, the battery performance will drop down, and we'll either need to dispose of the battery or recharge the battery. A fuel cell is a battery that we are constantly fueling, right? We're constantly adding fuel to that battery, and so it never runs down. And so one of the applications of fuel cells has been in sort of backup energy or energies of buildings where we don't want these sort of shutdowns when you have to go through recharge. So obviously, as you know, a lot of times cell phone, it's less available to use when it's in a recharge cycle, right? And so if you are recharging your batteries, then you're not getting that nice stable output, right? If you can imagine that as long as you keep supplying fuel to your battery, that it just keeps running, right? Then you never have that sort of downtime that you might have with a recharge cycle. So the output in these is about the same as sort of your typical batteries that we've seen besides the lithium-ion battery and the lead storage, about 1.2 volts, so kind of on par with the nickel metal hydride battery. The anode and the cathode are typically platinum coated metal, so they're typically platinum that has been coated with some sort of catalyst to help the reaction along, or to cause your electrolyte, again, is a hydroxide-based solution, so it's a basic environment. And in the most basic example of this, which is what we call the hydrogen-oxygen fuel cell, the hydrogen, right, the anode, this is the, quote, fuel, right? So this is what we call the fuel in the fuel cell. And we have hydrogen that comes in, and that hydrogen is being oxidized from hydrogen 0 to hydrogen plus 1 at the anode in the presence of your hydroxide ion. At the cathode, you have oxygen coming in the other side, and that oxygen is being reduced from, again, oxygen 0 to oxygen minus 2 and forming hydroxide. So we can see the cycle here, right? So if you look at your overall reaction here, we have 2 hydrogen plus O2 to give water. Sorry, there's a typo here. That should just be 2 waters. Got too many waters there. Okay, so we got our basic hydrogel. Now, this is the most common. You will see other versions of this where the anode has been changed, right? We're using a different fuel, such as methanol or ethanol, or various other types of materials that can serve the same purpose as the hydrogen can. So that's where people sort of do research on the different formulations in these batteries. The oxygen is a pretty constant part of this battery. Now, while we don't see a lot of applications of fuel cells yet, mostly in stationary applications, we would love to use these in, say, like vehicles. Obviously, the big trade-off here, a battery is a self-contained, right? Whereas here, you would have to have fuel, right? You would have to carry fuel with you, and that would have to be in some sort of tank. Now, carrying hydrogen gas in, say, a vehicle has its own issues with the flammability and low density, right? You can't carry that much of it. And so there's issues in fuel supply here. But other places have found applications of this, as I've said, in stationary applications, buildings, etc., but also in breathalyzers, right? These are probably the most common everyday use of a fuel cell, whereas these handheld breathalyzers are taking advantage of a fuel cell where your fuel here is the ethanol. And so you breathe into this, the ethanol functions as your fuel. You're getting oxygen from the air here, and the more ethanol you have here is going to cause this fuel cell to run. It's going to supply fuel, and as this runs, it's going to give off a voltage, and through the electronics here, this voltage, the amount of voltage you get off, or the amount of electrical signal you get off, can be correlated to the amount of alcohol that the person is putting into that, or how much alcohol they have in their breath. Okay. So batteries, fuel cells, one application. So in the next little section, we're going to talk about the other type of other type of electrochemical cell that we haven't talked about, and these are what we call electrolytic cells, or electrolysis.